This is Lab 4, the Spring Mass Lab. The objective of this lab was to analyze the motion of a spring mass in which the mass was swinging in an arc while oscillating on the spring. This was done using some of the fundamental principles of physics, such as the momentum principle, the energy principle, and Hooke's law. I used V idle to predict the motion of the spring mass and make comparisons. The results were that the predicted motion of the mass follows the same pattern as the data obtained from Tracker. I also concluded that the spring mass system does satisfy the energy principle. The two main physics principles used in this lab are the momentum principle and the energy principle. The momentum principle is used to predict the mass's new velocity and position. The energy principle states that the change in energy of a system is equal to the work done on the system by the surroundings. Our system includes the mass, the spring, and the earth. Hooke's law is used to calculate the spring's relaxed length and stiffness. I used Tracker to extract the position data of the spring mass as it oscillates. I used this data to get the initial position of the spring mass, which I used in my model. I also plugged in the mass, which is 0.402 kilograms, and the initial velocity, which is 0 at time equals 0. Then I calculated the spring constant. To do this, I used the data from Tracker to find the period and solve for the spring constant, which I found to be 6.86 kilograms times meters per second squared. I used this value to determine the stretch of the spring, which I found to be 0.574 meters, and used that value to find the relaxed length of the spring, which is 0.126 meters. I plugged these values into the code here to be used in the model. L hat calculates the direction of the spring mass, and S determines the stretch or compression of the spring, which is used to quantify the spring force. Next, I calculate the energy values of the system. The components of the system are the mass, the earth, and the spring. To calculate the kinetic energy of the mass, I used the equation 1/2 times mass times velocity squared. I calculated the potential energy of the earth using the equation mass times gravity times height. The potential energy of the spring is calculated using the equation 1/2 times the spring constant times s squared. I then plugged these values into the model here. Next, I calculate the force of gravity by multiplying the mass times gravity. I calculated the force of the spring by multiplying the spring constant times the stretch times L hat. The net force is the sum of those two forces. I used Newton's second law to update the velocity of the mass, which I then used to update the position of the mass. The new position is used to update the spring. The new length of the spring is used to calculate S, which tells us how much the spring is stretched or compressed. I will now run the model. Here's the output when the model is run. The blue arrow represents the spring force and the black arrow represents the gravitational force. The blue ball represents the spring mass. The graph shows all of the energies of the system. The blue line is the change in the kinetic energy, the red line is the change in the potential energy of the spring, and the green line is the change in the potential energy of the earth. The yellow line is the sum of all the energies, which is 0. I will now move on to the discussion questions. First, I will explain whether or not the energy principle was satisfied. The energy principle states that the change in energy of a system is equal to the work done by the surroundings. Because each component, the spring, mass, and earth, are all part of the system, there is nothing in the surroundings, and there is no work done on the system. Therefore, the change in energy must equal 0. As you can see, the yellow line in the graph, which is equal to the total energy of the system, remains at 0. The energy principle is satisfied. The next question asks for a comparison of the periods of the oscillation of the x position versus the oscillation of the y position. These two graphs compare the two different oscillations. I found the oscillation of the x position to be 1.66 seconds, while the oscillation of the y position is 1.53 seconds. One oscillation in the x direction takes 0.13 seconds longer than one oscillation in the y direction. The periods are different because the equations for the oscillation in the y direction uses the mass and the stiffness of the spring, while the equation for the oscillation in the x direction uses the length of the spring and gravity. Thank you for watching.